Okay, welcome to our next talk by Professor Henri Moscovici on semi-local adelic prolate operators and Sonin spaces.
Okay, thank you very much. All right, so as Alain explained very clearly, there are these concepts, notions, like prolate operator and Sonin space. I don't want to call them tools because it sounds demeaning. We call them we call them players or actors, something else, not tools. Okay, so in order to advance the program, which Alain started in '96, we have to get involved in this semi-local framework. You can also call it semi-adelic because semi-local is used also in other parts of mathematics, and it can create confusion. But that's why sometimes we are adelic, this adjective to that. All right, so I'm going to talk about the joint work with Alain and Katia Consani, which is promoting these actors to the level of the semi-local framework. But in addition to, okay, what's in the title, I have to start with another gadget, which also formulated by Alain, which is not a spectral triple. It is only a pair. It's called cyclic pair, because the cyclic pair, the table of contents is irrelevant. The cyclic pair will be a good envelope for the notions which I'm going to talk about, which are extensions of the prolate operator, correct? Parts of it. So that's a definition. Simple enough. I mean, it's a pair made from a self-adjoint operator, D, acting, of course, on a Hilbert space, countable dimension, and a cyclic vector, which is in the domain of all the powers. And it's cyclic, and it's of norm 1. It's cyclic in the sense that if you take the linear span of the first n plus 1 powers, because you start with 0, and you call it En, the spaces form a net which is dense in age. Okay, now, the cyclic pairs also come with this grading device, and we call them even, like in K-theory, but it has nothing to do with K-theory yet. So such a cyclic pair is graded when you have a Z2 grading, which is as always a unitary of square 1, but which anti-commutes with the operator, but it keeps the cyclic vector psi fixed, I mean this generator. All right, to this, we add a number operator in a natural way by just, first of all, by Gram-Schmidt, you get an orthonormal basis out of the powers of D. And the number operator then is defined naturally just by taking the number given by the index of the vector in the orthonormal basis. Now, a cyclic pair, okay, it's an abstract notion, but in fact, it can be put in a canonical form, namely, there is a probability measure mu on the real line and a unitary isomorphism from the Hilbert space to the L2 space with respect to this probability measure. Oh, sorry. Satisfying these three conditions. First of all, this transformation U sends D to multiplication by S. S is the running variable on the real line. It sends the cyclic vector psi to the unit 1, and it sends the En, of course, to the space of polynomials of degree less or equal to n, because D went to S. And the spectral measure, which is determined by D, psi is a complete invariant for the cyclic pair. Finally, it is even, and now you can see why it's called even in this case, because it's even if and only if the measure is even. So that's the grading, and the grading is then the natural one, just even and odd in terms of the index of the orthonormal base. What? You mean, okay, this is for any f, not just polynomials. Okay, so, but yeah, you will see it on the next slides. You are right in some sense. It's the moment will come into place. So to such a cyclic pair, you can associate, or we associate a formal prolate operator just by adding to the square of minus square of D the number operator. And this, as you shall see soon, will be our sort of first candidate for the extension of the prolate operator using this formalism of cyclic pairs in canonical form. Okay, and indeed, there is a moment problem which is associated to a cyclic pair, because, but in this moment problem, you don't start with a measure, you start with the self-adjoint operator of the cyclic pair, and you take the moments which are defined by the corresponding measure. And then you get the moment problem, which is a von Neumann solution. In fact, I mean, dig side, the measure itself is a solution to a von Neumann problem. Von Neumann is the same as extremal solution because it's a convex set, all the measures which satisfy this moment. Okay, now when you have a moment problem, you have associated orthogonal polynomials, which we already introduced, in fact, and you have the corresponding Jacobi matrices with respect to the orthonormal basis of orthogonal polynomials. And then the matrix is coming from the fact that you have this kind of, this relation, d of psi n is only a linear combination of the successor and the predecessor, because by Gram-Schmidt you killed the rest, and the fact that d is self-adjoint. So you get this matrix, which, all right, in it's Hermitian, because d is self-adjoint. And by just, if you want, and we'll do that by a global change of phase, you can make all these coefficients to be real numbers and positive. Okay, so Now we had the associated formal prolate operator, and that one also has a matrix, but the matrix on the diagonal, it will have these extra terms, because remember we are adding the number operator multiplied by lambda. And so it will be seen in the matrix, and the off-diagonal elements, they are still Jacobi matrices, but with a diagonal. And there is an even part and an odd part, because we are talking about an even spectral triple. All right? Okay, now we get to the operators which were mentioned in Alan's talk, and which are the main actors, really. The first one is the scaling operator. So the scaling operator is, well, capital H is the scaling which Alan introduced on L2 of R. We are taking the even part. And then S is made like this because you want to deal with a self-adjoint operator. And it's acting on L2 of R even. And yeah, it's a generator of the scaling, this is. And so now what we want is to put this, it defines a cyclic pair. It will be an even cyclic pair, which we want to put in canonical form. But in order to put in canonical form, well, that will be done by an isomorphism. Oh, sorry. By an isomorphism, which is made of two pieces. I mean, one of them is this integral called U of f, which is, I think part of it appeared already in Alan's, on Alan's slides, but this one is, has, oh, I'm missing an S in the formula UF of S. And then you multiply this integral by a normalizing factor, which is the following. You take the first eigenfunction of the, well, Hermite operator really, H0 of x, I mean the ground one, oh, sorry. And then the measure, you normalize the measure by this factor. This is what turns out to be the good transformation. So after Alan found it, in fact, we saw that Hardy and Tishmarsh used this type of transformation. That's why we call the whole thing the Hardy-Tishmarsh. In a paper from 1930, they were using it. That paper tried to give a characterization of the self-reciprocal functions, self-reciprocal with respect to the Fourier transform. So when you deal with the Fourier transform and you look for such things, this is the transformation, the kind of transformation which naturally comes in, and that's exactly what we are doing here. So the cyclic pair of the scaling operator with a, when I say the cyclic pair, I also have to add, for the vector psi, cyclic vector, that will be H0, you will see. Yeah, it's on this first thing. So the cyclic pair is, S is the self-adjoint operator, psi, we call it psi infinity. Infinity doesn't signify something far away. It just signifies that we are at the Archimedean place yet. We didn't, on the real line, we didn't go into the Pleiades. So it's H0. So this is a cyclic pair. It's an even one. And the grading, which is unique, in fact, it's the Fourier transform. This Fourier transform, the usual one. And the Hardy-Tishmark transform V puts this cyclic pair in canonical form. So what does it mean? It means that, it means that it will take D into multiplication by S, and it will take these Hermite functions, which will give an orthonormal basis for, well, we'll see. For the operator, after completing with the number operator. So the number operator of the cyclic pair happens to be the Hermite operator, well, divided by 8 pi, minus 1/4. Hermite is the Hermite which I wrote over there, whose eigenfunctions are the even Hermite functions. And now if you compare it with the standard prolate differential operator, the one which was mentioned by Alain, that those people from Bell Labs have used, and this operator being known from the work on the ellipsoid with the, as Alain mentioned, with the Laplacian. Okay, if you look at it, you see that this lambda, this parameter lambda is running. I mean, it can be fixed anytime at 1, for instance, but we keep it there from the beginning. Now, if you just look at lambda squared times d by dx, sorry, where is that? Okay, you get lambda squared d by dx squared with a minus sign plus 4 pi squared lambda squared x squared. That's the Hermite operator. So you see why, well, in fact, there will be something else coming in. So you'll get the Hermite operator minus 1/4. So this W lambda, in fact, it's exactly what comes out by completing the cyclic pair with a number operator, the cyclic pair being the scaling cyclic pair. And then if you conjugate by the Hardy-Tishmark transform, everything, so since the scaling moves to minus s squared, well, it really minus s squared, there was a minus 1/4 in the number operator which appears, and so you get altogether the formal prolate operator is just the ordinary prolate operator in this case. It's moved into this guy after you put the cyclic pair in canonical form, in this canonical form. Okay, so if we look at the isometry, this Hardy-Tishmark, we see that it takes the Hermite functions, that was the whole point, to orthogonal polynomials. Because the Hermite functions were a basis for L2 of R even, orthonormal basis. And we take the even part. And the matrix associated to multiplication by S is a Jacobi matrix, Hermitian Jacobi matrix. And again, it has where is it? These entries. But if you change the phase, global change of phase, it becomes the symmetric matrix, where ANs are explicit and they are of this form. I mean, they are exactly this. Okay, so this is what becomes of the scaling operator after you put it in canonical form. Now the Jacobi matrix for W lambda, well, it has two restrictions to be a Jacobi matrix. You have to restrict to the even part and the odd part. In each of them, it is a Jacobi matrix, because the Jacobi matrix is three-diagonal only. So if you put everything together, it will have some zeros in where you don't want them. ANs now, they will come with plus and minus to indicate the even parts for the even component of the Jacobi matrix and for the odd component, and they have now these expressions. As you can see, the diagonal part involves lambda, as it should, because the diagonal part brings in the number operator. Okay, so this is sort of standard type matrices in the moment problems, Hamburger moment problem, Stilges moment problem if you work on the half line, all these things. Okay, so now I explained what happens with the scaling cyclic pair in the Archimedean place on R. We want to promote everything to the semilocal framework. And so I'm just repeating what Alan said about the semilocal. So you take a finite number of primes in everything which follows this sets S, finite set S of primes will always contain infinity, except when in some formulas we want to remove it. Now at each place you have a norm or modulus, which is can be extended to the semilocal product in the absolutely natural, normal way. Now, Q sub S, I mean, these are the adels for the global field is the field of rational numbers. So the S adelic part of the adelic completion, is Q sub S. And it's A sub S. And now Q sub S is the part of Q in which this modulus or norm is less than 1 or equal to 1 for all the places or primes, in fact, which are not in S, which means that the denominators involve only the powers of P, P being V, if you want. The same thing will be at place P. And I recalled here what the p-adic norm is, which immediately gives you this definition, makes it clear. And then we take, so AS will be the adelic class, not yet. The big piece of the construction of the adelic class space. We need a discrete subgroup. This will be the invertible elements in QS called gamma S. So they are over there. And now the semi-local adel class space is the quotient which Alan already mentioned, which is a non-commutative space as soon as you add more than one prime to the Archimedean place. You have a projection, and the modulus, or the norm, whatever you want to call it, descends to this space. The invertible element GL1 of this AS, of the AS, is the product of GL1 of QPs in S. And on the other hand, if you take the GL1 of AS and divide by gamma, this is a good space. And this space, I mean, it's a group. So it acts by multiplication on the orbit, on XS. And you can view it as a subset of XS if you embed it as the orbit of the unit. Okay, so that's a setup in which you want to define the corresponding Hilbert spaces. For the AS, there is no problem to define L2S because you have Haar measures on every L2 factor. L2 of CS is also defined in a natural way because you also have invariant measures. And L2 of the adelic class space, it's a little bit like Alan mentioned. You have to be careful because you have some zeros, but measures theoretically, they can be identified. But in fact, there is a canonical isomorphism. I call it WS from this space to L2 of the ideal class space. This one is it would take a while to write it exactly what it is, but it's in Alan's book with Mathilde, for instance, and probably in your paper in '99 also. Yes, it's okay. And this isomorphism WS also descends down if you take the K invariance. K sub S is the maximal compact of CS, of the ideals. Because the ideals can be viewed as a Cartesian product, non-canonically. But this gives rise to the identification eventually, which you see on the last line here. The K invariants in this adelic class space are isomorphic with L2 of the multiplicative part of R plus with a Haar measure, which is d star u is du over u, of course. All right, so now the first theorem comes, but I still need some notation. RS is the maximal compact subring of. Now we are removing the infinity of the finite adelic part. And eta S is something which is defined here by taking any function in L2 of R even, and then you multiply it, you take the tensor product with the characteristic function of indicator function of this maximal compact subring. And then you take the class means modulo gamma. I mean, you go down. Okay. And now another piece of notation is we need a multiplicative Fourier transform. And it's just the natural one in this context, for each, well, you have to, the measure mu is fixed. So that's coming into the definition of US, the part of the Hardy-Titchmarsh, the main part of the Hardy-Titchmarsh, there is a multiplicative constant in front, as you may remember, which will come in. So we have the, we have the US. We have the US, it's taking this eta of S into what you see here, this product. You apply the Hardy-Titchmarsh transform, the one in the Archimedean place, only to the function f. That's the point here. Well, U is not the Hardy-Titchmarsh yet, it's B. B is the Hardy-Titchmarsh. It will become clear, yes, on the next transparencies. But in between, f of s commutes, eta of s is, this map is equivariant with respect to the Fourier transforms. Okay, now we need another factor. I call it ms of s, but it's E bar of s, inverse of something. E bar means conjugation. We'll see the reason I put a bar a little bit later. So let's call it like, let's take it as a notation. And then you take this measure with this Radon-Nikodym derivative and form the Hardy-Titchmarsh by combining these two parts, the U of S and the M of S, which is multiplying by this factor. This is a product of the local factors coming from the finite places. And when taken together, that's giving the analog, the semilocal extension of the Hardy-Titchmarsh, which gives the canonical form of the cyclic pair extended to the S adels. Of course, you have a grading too, and the grading is the Fourier transform, f of s, which becomes, after you put it in canonical form, it has to, if it's canonical, it becomes S goes to minus S, because the measure was the one which was ds. Okay, now this diagram shows the relation with the Archimedean place. So the Archimedean place is on the left. So V was the Hardy-Titchmarsh. This is the extended Hardy-Titchmarsh. Eta is the unitary which identifies the upper part. Here, the lower part of the diagram is not a unitary isomorphism, but it's bounded and the inverse is bounded. So it's a Hilbertian isomorphism, not an isomorphism of Hilbert spaces, but of Hilbertian spaces. Okay. So that's the extension of the cyclic pair. Now, the number operator, well, let me remind you that the semilocal, the semilocal Hermite operator applied to the S, which is only the singleton, the Archimedean place, is just the N which we had before, which was the harmonic, the Hermite operator. Well, and then you associate to it something, you add, divide by 8 pi, add some minus 1/4 or something, and get N. But now we have NS for any S, not just for infinity, on the right-hand side of the diagram. And the eigenfunctions of the new number operator NS are images, are pushed from the like we dealt with the Hermite functions, moving them by the Hardy-Tishmar, moving them on the right hand side. Now we move them by this eta onto the right side of the diagram. Okay. So PS were the orthonormal bases of polynomials obtained by the standard orthonormalization. And so the emerging candidate for the semilocal prolate operator is the sum in which I see a typo, minus S squared. Now I lost the minus sign. Every time I look at my slides, I see a typo. That's the first one. The other part is okay, but there was an I in the, yeah, forget about the middle part, because the IS was equal to H plus 1,000. I squared is minus 1. So at least half of this formula is good. Okay, the dual Hardy-Tishmar transform will come into play too. And what is the dual Hardy-Tishmar? You know, I use the notation E bar before because E of S will be now the conjugate of what was E bar. So this changes the sign of all these local factors. That's called ES. And okay, multiplication by this factor ES, let's call it beta, will come into the definition of the Hardy-Tishmar isomorphism, well, in the dual setting. So the dual Hardy-Tishmar, by definition, is the isomorphism which you get in this way, namely composing US, which was defined before, with multiplying it by a factor. So all these transforms come in these two pieces. One is just the multiplication, and the other one is the series one. Okay, so you also have a compatibility. This duality is given by the clear fact that we took a measure, I mean, with one radon Nicodim, and then inverted it, and then when you pair them, it will disappear, so you get a sesquilinear pairing like that, which is non-degenerate. And now I can come to the definition of the Sonin spaces. Well, this definition, I mean, it's not new. I mean, it's the definition of the Sonin spaces, which is the natural extension of the Archimedean Sonin space for the p-adic case, and Alan already had it in his papers. So the Sonin spaces can be defined in the semilocal case, naturally. In fact, the primes, I mean, it will not be seen in what I'm going to talk about, but there is an important distinction because the Sonin space, the invariant part under the compact subgroup Z star P, has dimension 1. This is something which is special for the finite primes. Okay, so let's look at the Sonin space in the semilocal case with the Fourier transform defined by, as I mentioned before. That's the definition of the Sonin space in the semilocal case, of course. Now, sigma of S, which was the last paragraph in, I mean, which includes sigma P, which I defined in the last paragraph, gives us a map theta S from the L2R even to the L2XS by just taking the class of sigma S tensor F. This is sort of looks like similar to the eta map, but it's a different one because now you don't take the characteristic function of some compact thing. You get you take this sigma of S, and this also is equivariant with respect to the Fourier transform. Okay, so you have this. And now I have to show some more formulas for if F is in the Archimedean Sonin space, then theta S of F moves into the local Sonin space with the same parameter lambda. And you have this relation, which is telling you what happens with the Fourier transform composed with the isomorphism between adel class space and adel class space. Okay, so we have these formulas here, and you see that what is added when you add the primes, you are adding, in fact, this factor, which is quite nice. It's the local factor, inverse of the local factors of the p-adic places. And now the significant result here is that the map theta S, so defined, is a Hilbertian isomorphism. So it doesn't preserve the norms, but it preserves the Sonin space. As Alain mentions, we believe that the Sonin space plays the role of a cohomological function. And so it's important to see that this remains stable as you progress. So the Sonin space as a set, theoretically at least, is independent of and Hilbertian space, but in fact it's more than that. And this is the link with the branch spaces. Because in fact the Sonin spaces were called Sonin by the branch. One of the chapters or sub-chapters of his book on Hilbert spaces of entire functions is called Sonin spaces. He writes with a French spelling. The Sonin was Russian, so you can, in English it would be without final E. Okay, so the Sonin spaces defined as before in the Archimedean place are realized as Sonin spaces in the branch book by the branch himself. I mean, he wrote this transformation. Okay, it's a sort of mail-in amended by this gamma factor, which takes isometrically the Sonin space defined before on the real line onto a Hilbert space of entire functions, which satisfies the three axioms of being the branch space. And the norm of this Hilbert space is given by, I mean, the L2 norm is given by this E infinity function. I defined E for any place. So E infinity would be the gamma function of something on the line 1/4 plus IS/2. Okay? So the L2 structure, the inner product of the branch space of entire functions is computed only on a line. I mean, you restrict it to a line because they are entire functions. And so that's the link in the Archimedean place. But now, since we had the stability result before, what we see, and these diagrams, this diagram, which is a commutative diagram, you see, oh, sorry. You see that theta of S is an isomorphism of Hilbertian spaces. This is the theorem here. But you also see that this is compatible with the identification à la Desbranches with spaces of entire functions. So this lower part of the diagram, they are genuine Desbranches spaces. The identity map is identity sets theoretically, but it's also Hilbertian. It doesn't preserve the norms, which is good because in a way we don't want, I mean, everything to be like in the Archimedean place. So what changes are the metrics. Okay, and they are all inside this lower part of the diagram. These spaces are subspaces of this, if you restrict to that vertical line. Okay, and now I come to the last part of what Alain talked about. In this last part in my talk too, which is a metaplectic representation. So as Alain already mentioned, the infinitesimal, the metaplectic representation, as you will see, was in the background hiding, but it in fact controls the situation pretty well, because first of all, okay, the differential of it, which I call infinitesimal representation here at the Lie algebra level, has the main part of the prolate operator, which already was playing a big role. So this is a standard basis in which H is the matrix. These are all 2 by 2 matrices. So H is diagonal matrix 1 minus 1, 0 of diagonal. E plus and D minus are with 0 everywhere except in one corner, lower corner for E plus 1 and E minus. So that's a standard basis of SL2. So the infinitesimal, the metaplectic representation takes little h into capital H. That's a capital H, or IS. It takes E plus into x squared, which is a nilpotent, and it has the opposite nilpotent, upper diagonal, into, oh sorry, into the square of the derivative. So you see, that's a sort of unusual representation, because usually you expect the Lie algebra to go to differential operators of order 1, because you start with the Lie algebra, not with the higher parts of the universal enveloping algebra. The metaplectic is special, and it takes care of the 2 parts of the prolate operator. And in fact, any representation which is known to be a representation and which is defined on H, which is a generator of one cartan. The other cartan is generated by what I call K here. K is E minus E plus multiplied by I. So any representation is completely determined by the values it takes on these 2 guys. One represents the compa cartan, and K would represent IK. The generator is the E to the ITK. You get the compa cartan. The other one is the split cartan. So behind the prolate operator was from the beginning this metaplectic representation, and in fact this is seen even better. Well, I put it what I said. So you get it's seen even better in the form that you can write a sort of formal prolate operator directly in the universal enveloping algebra by taking H squared plus a multiple of K and something. And this goes through any representation, not just through the metaplectic, but through the metaplectic you get exactly the standard prolate operator, which is in boldface. Okay, now the point about the metaplectic is that it's not a unitary. It's not a unitary representation of SL2. It's a unitary representation of a double cover of SL2. That's why it's called the Siegel Shale Veil representation. Siegel and his former student Shale dealt with this representation in the infinite dimensional setting, Hilbert-Schmidt kind of thing. They started from something in mathematical physics, Siegel. And but Shale was able to go from the infinitesimal form to the integrated form, even in that context. And by the way, that context was something which is also related in spirit. I mean, because we're looking for a Klein-Gordon operator. They were working with a Hilbert space made of solutions for that kind of equation. Okay. All right. So the metaplectic representation lifted to the double cover looks like this. Well, in the over R. Now, I didn't explain, okay, this is easy, I mean, to exponentiate H and E plus. But you have to define the representation, you need to either exponentiate E minus or write something else. Well, there is an element which for SL2 is called the Weil element, which plays Weil, not Weil. Weil element, which is moved to the Fourier transform. But up to a factor, gamma, which I will not explain because that's not easy. You get it. It's a co-cycle representation, in fact. And if you want to write explicitly as a unitary representation, you have to write a full other slide. And doesn't matter so much for now. But anyway, what I want to say is that this, what did I put here? Oh, this is not pi, it's bar pi variation. This omega of W, that's another typo. Takes W tilde. W tilde means that you lift it to one of the two things, the fiber. And gamma reflects the W tilde. But gamma is always something of absolute value 1. Usually it's plus minus 1. But, okay, so that's the metaplectic representation for R. It has two components only. So if you decompose it as an irreducible representation, it has an even part and an odd part. And remember that from the beginning, we were working, so this is the representation in L2 of R. And we are working on L2 of R even everywhere for the Archimedean place. And this is what was in the back. Now, if you want to see how closely related to the situation is, you can check the, for instance, the commutation of the Fourier transform with the prolate operator directly at the level of the Lie algebra prolate operator. Because if you take, these are calculations with 2 by 2 matrices. You take the W element, is like 0 on the diagonal, 1 and minus 1 on the off diagonal. And you take the adjoint, means that W is not an element in the Lie algebra, it's in the group SL2, well, SL2 tilde. You multiply it left and then the inverse right with H, you get minus H. You do this with K, you get K. So it preserves the formal W. So the point now is that this metaplectic representation was extended by Weil after these guys, Siegel and Shale, to the context. You can take any field and its Poincare dual of the field and then make up of this a symplectic data, and to which you associate the symplectic group, and the symplectic group has a double cover, which is called the metaplectic group. And in fact, this double cover of SL2 is also called metaplectic. And you have the representation, but this works now over any field, any local field, and we can extend it to the, like Alan already mentioned, to the semilocal easily. And okay, it works fine with our candidate of the prolate operator, but it could work even better with another candidate, which will take advantage of the fact that the subtlety of this representation is in this x squared, the quadratic thing. Because this is what they used, for instance, to reformulate the quadratic reciprocity theory, which started from Gauss and then Hecke and then Hasse and Hilbert, and he put it in sort of definitive form by using exactly this kind of things. So that's where the story ends for now.